Our, uh, our next presentation is from Andreas Hildebrand from ALC Networks. And I just love the title here. You know, your flight will be delayed by 5 milliseconds. So I'm anxious to hear what you have to say. Take it away, Andreas.
Okay, thanks, Wes. Thanks for stopping by. I'll try to keep the presentation time so that the flight won't be delayed further than 30 minutes. This is the time slot. So let's jump into the topic. It's about latency. So what is latency? Wiki defines latency. What? Here, no. How's this working? Wrong side. Latency is a time delay caused between the cause and the effect of some physical change in a system being observed. So that's just directly taken from Wiki. And of course, the latency is also a consequence of the limited velocity of any physical, how fast any physical interaction can be propagated, which, by the way, is always less than the speed of light. So can't beat the speed of light, right? So if we talk latency, speed of light is one of the fundamental issues. Now, let's look into a traditional signal distribution. We all know these kind of things, right? Analog, digital, cabling with AS3, MADI, SDI. And we have typical use cases for that, like, let's say, a venue which has a number of microphones with I/O boxes and an audio router, an equipment room, and mixer, and a production stage, some processing, then a transmission. And basically, if we look at any particular individual signal, we can follow a direct path from the source to whatever destination. And this is what we call a fixed connection between the microphone and any related output. The benefit what we had with this kind of technology is that we always have a fixed and deterministic latency, right? So we don't have to worry about latency, about changing latency pretty much. It's always determinal and fixed. And the fundamental technology is basically circuit switched routing, right? That's what we do with router and all these kind of things, and everyone is used to it. And here's another nice example of circuit switched routing, which analyzes the same physical principles. And the only thing we need to really worry about is, again, signal travel times at the speed of light, basically. So let's have a quick look into a table. I compiled a few data sets here. As long as we are staying inside one facility, as you can see from the first two entries, we actually don't have to worry about this latency, right? We are staying in microsecond latencies. That's not a big deal, not even with audio. If we go, cross country, let's say New York to LA, well, there's a 13.3 millisecond theoretical latency. We will have a bit more because we will have some switching and conversion equipment maybe in between. But again, we are in the milliseconds latency range, and latency with this kind of technology only starts to matter if we are going, to the moon or even interstellar, right? And that's certainly not an application case for AES-672110 or whatever. Anyway, so that's the traditional signal distribution and what we are doing with networks, with network media distribution. In contrast to the circuit switch routing, we are now into packet switching. It's a fundamentally different technology, right? And packet switching, you know all what packet switching is, right? You have seen that before. You experience it day by day. Packet loss, delay variation, rerouting of packets, all these kind of things. So here's a quick illustration how packet switching works. We have a sender, a receiver, we have a meshed network, and if we want to send information from the sender to the receiver, well, we have a packet which is nicely wrapped. It has a destination address, and it's handed off to the transporting company, the network. Whatever route it takes, at some point in time, it reaches the destination. If we send off another packet, it may take a different route through the meshed network. And as a consequence of each packet basically being able or potentially can take a different route, there is no fixed connection anymore through the network, right? In contrast to circuit switching, we always have a fixed connection, and packet switching, this fixed connection is gone, and thus the latency may vary through a network. So, having set the scene for the difference between circuit switching and packet switching, now what actually does latency mean for packet switched operations, for media networking, for AoIP or video over IP? What are the determining factors for latency in packet switched environment? Well, first of all, the underlying networking technology matters. Very easy. I mean, if we have a slow network, like a fast Ethernet network, that definitely takes longer for information to propagate through the network than with a gigabit Ethernet network. And the higher the speed, the lower the latencies or transmission times are actually. So network speed is one of the determining factors. And I've highlighted gigabit Ethernet because that's the most common technology for en route connectivity. Yes? 40 gig? Oh, yeah. Good. Good spotting. I need to correct this. Thank you. Of course, the type of switching routing equipment is what? Yeah, 1 point. I guess it's just it's the com. Yeah. Right. Whatever. I'll do the math again. The type of switching is important. Well, usually we have hardware-based switching or routing fabrics. They are of course fast with less latency delays. We have software involved in some routers, especially it comes to firewalls or filtering mechanisms. We may have mixed environments, of course, and we also have cutting-edge technology which do store and forward, which do cut through in contrast to store and forward. Traditional switch takes in a full packet, and then once it has it, is forwarding it. But we also can have a cut through, where the transmission already begins once the first bits of a packet have been received. So all these make, are factors of latency when it comes to the networking technology. Besides the networking technology, the network topology, of course, matters. Well, topology, for example, one of the points is the number of hops. So the more switches are en route of a certain path, the more time it will definitely take for a packet to travel across the network. So as a rule of thumb, if we are running gigabit Ethernet per hop, we will have approximately 1 sample time of audio and latency involved. It doesn't matter what the distance is. Even if it's just a short patch cable, that's the time a packet needs to traverse, a fully fledged packet needs to traverse a gigabit Ethernet switch. At least. That's not the maximum time, that's the minimum time. And I just mentioned another number, the 1 millisecond transient time happens if you have 4 hops at the fast Ethernet. In some places we see fast Ethernet, just to give you a number. So rule of thumb to remember, 1 sample time for 48 kilohertz at a gigabit Ethernet switch. So unfortunately, as I mentioned, that delay is not static due to dynamically changing traffic situations. I will come back to that in a second. Of course, speed of light also, again, matters when it comes to distance. As soon as we are running outside a corporate environment, long distance, speed of light comes into game again. Again, this is the table we had before, and you see some empty lines there. And I will now fill some of these lines just, for giving some ideas. As soon as we cross the 6-kilometer line, we'll have another sample delay just because of speed of light. Right? Because the packet needs that time to rise. And if it goes 300 kilometers, it's already at 1 millisecond latency. And that happens to coincidence with the mandatory packet time in AES-67. 1 millisecond. We'll come to that in a second. Or in a minute, basically, not in a second. So distance matters if it goes to wide area network applications. Here again. Okay, then one thing enters the game which we don't have at circuit switch routing, that is network jitter or packet delay variation. And variation already indicates, we are not going to have fixed or deterministic delays anymore. So what's packet delay variation or network jitter? How does that occur? How does it look like? Let's assume we have a transmitter who is sending out audio packets at a nice distance of 1 millisecond. Well, we choose 1 millisecond packet time. We have a full packet. After 48 samples, we're sending it out. Every millisecond, there will be a packet appearing on the network interface. So that's how this looks like. We have a nice equidistant transmission of packets from the transmitter side of things. While on the receiver side of things, there will be a transmit delay, of course, the network transit delay. And wouldn't it be nice if the receiver would see the packets equally equidistant coming in? Well, unfortunately, that's not the case because there's a network in between, and we just don't know what actually is going on a network. So what actually happened is that we have network jitter, which we need to take into account now. And unfortunately, that means that packets now not coming in seen from the receiver on the equidistant basis, but they come in a bit slower, a bit faster. Over a longer time, there will be, of course, a packet every millisecond, but from packet to packet, we will have differences, variation, packet delay variation. And that we definitely need to cope with in our application. We need to understand this. So what is causing or influencing packet delay variation in a network? Well, again, switch performance. As I mentioned earlier, if we have hardware, there will be just very little packet delay variation due to the technology. But if software is involved, well, software has varying processing times. And if a packet needs processed by software, we will have varying delays, right? The number of hops and the routing, of course, are causes for packet delay variation. For example, in a mesh network, the routing may change. Once of a sudden, packets are routed a different way, and thus we have an increase or decrease in the overall delay. Or the number of hops may change. The network speed may change in between, which also affects. If we have a traversal from a gigabit to a fast Ethernet link, that also may affect or cause some packet delay variation. So basically, this is something one needs to understand when it comes to the causes of packet delay variation. And then, which is much more important than the technology parts, is the bandwidth utilization. Now that sounds maybe not, quite obvious at the first glance, but let's have a look at this. We have a switch which has which is hit by a number of different flows. Right? Could be audio flows, data flows, whatever. And we want to all put them down to one destination port, to, whatever, a link to the next switch or whatever. So what usually happens is there's a multiplexer which gathers all the incoming packets and lines them up one by one after the other, in the output or egress queue. And then there's an egress, mechanism which then forwards a packet whenever it's there appearing in the network queue. So what may happen if we look at this particular image is we see that we can use this, that the packet number on row 4, number 6, is lined up at the end of the egress queue. The egress queue is full, so the transmitter is working on it, but that means that the packet has a longer transient time, let's say as the packet number 4 coming in. So that means the more packets are waiting in an egress queue, the more delay is being built up at that very moment for a particular packet. That situation may change in the next, next millisecond when there is enough empty room in the egress queue again, because lots of packets have been sent out and none of the next packets are have that destination. So the queue empties, another packet comes in, and that's even, pushed out earlier than the other packets of that particular flow. That all happens if we don't employ the magic scheme of quality of service, because quality of service can do wonderful things in that respect for us. So let's see how this works with quality of service. Again, when we employ quality of service, we have our different flows on the left side. We have now not just one egress queue per switch port. We have a number of egress queues. Usually you have 4 or 8. I just visualized 3 of them with a high, medium, and lowest priority. And what now happens is there is a what we call a classifier which identifies the incoming packets by its importance, by its priority tag and sorts those packets into the related priority queues. So you can see, obviously, flow 3 is a flow with very, very important packets. All those packets are sorted into the highest priority queue. And then the medium priority queue, apparently these are audio flows. Packets go, regardless where they're coming in from, go into the middle priority queue, and then there's some low priority traffic which reach the lowest queue. Now the trick is that on the egress side, there's a scheduler, an egress scheduler, which always looks at the highest priority queue first. And as long as there are still packets waiting in the highest priority queue, it takes those and forwards them to the egress port. And if there's no packet waiting in the highest priority queue, it takes the next packet from the medium priority queue, and so on. So now we have a prioritization, and that can minimize the packet delay variation the higher the packets are in the queue. And for our, as we already know, for our AoIP or medium over IP, A672110, PTP packets have the highest priority. They are very small packets, originating or being transmitted quite seldom compared to audio packets. And so that means that our PTP packets receive very, very little packet delay variation, which is good because PTP mechanism or algorithms are very prone to packet delay variation. So QoS is something there which is nice, which works. By the way, QoS also works in other practical environments. You probably know this one. Yeah, I had that experience a few days ago again. Well, I was a passenger with a low priority tag, and guess what? I had to wait in the economy class queue. And there were constantly, passengers with premium tickets passing by. Well, even if the boarding for economy already started, and they were allowed to board just before me. So there's the egress scheduler, and she takes care of, allowing any first-class passengers board the plane. That's the single link, right? Board the plane first. What happens in the plane is another story. However, the whole differentiated services, quality of service does not prevent us from, from overflow situations if we have competing traffic. Now let's assume we have a quite high bandwidth flows with the same priority marking on 5 and 7, and they are all going to the medium queue. What may happen is that this queue fills up and the buffer will overrun because there's just no place for storing any of those data anymore. That may cause a switch to throw away packets in the overflowed priority queue. That depends on the switch implementation, actually, but I would just want to say quality of service is not necessarily a scheme to prevent packet drops. But it's a cure for the packet delay variation. And skipping over this one, I've developed a worst-case multi-hop calculation table where you can enter the number of streams and the format of streams, entering a particular switch port, then adding the number of competing streams, hitting that switch and going out to the same link destination across multiple hops, actually. And it can be interesting to see what numbers at the end are calculated for possible worst case, packet delay variation. And that's the reason why, in practice, as a good advice, if you're on an IP network, once your observed bandwidth reaches 50% of the nominal bandwidth or network link bandwidth, try thinking about increasing the network, the bandwidth link on that particular link. 50% as a medium, utilization is good. Anything which goes up might cause difficulties. As a rule of thumb, as a general purpose. Now, that is all network. Now, there's another important factor for latency. And that's the stream or packet configuration itself. This has nothing to do with packet delay variation anymore, right? We have the network technology. That was one point. Now we are, what is a stream? How is the stream packetized, formatted on a network? So we have formatting or encoding parameters in the AS67. Sampling rate, 48 kilohertz, is mandatory to be supported. We have the PCM bit width. Usually we use 24 bits. We have the number of channels we want to package into a stream. On this example, there's a left and right channel, and of course we have consecutive, left, right, left, right, left, right samples we are acquiring, and then the resulting stream is a series of sample flows. Now this has to go into a packet. But how many of them? We are not sending out a packet for each sample, right? We want to do that. That's where the most important parameter comes into game, and that is packet time. And as the parameter already indicates, this has to do something with latency, because time may be a varying thing. And what is that? Packet time describes the number of frames. Well, what is a frame? Audio engineers know a frame is the number of samples times the channels. So for the number of channels I have, all first samples of all the number of channels are one audio frame. Then the second sample with all channels is another audio frame. And this looks like this. So we have channel 1, channel 2, and channel N. And we have samples, of course, occurring at equal times there, and these are called a frame. So all the first samples of all the audio channels are an audio frame, and so on. So we have at the end a stream of frames, which again, if we look deeper, is a stream of samples, of course, right? This is how audio is being presented and processed. And packet time simply says how many of those audio frames go into the payload of an RTP packet. So theoretically, we can send a packet with every sample, or every frame, actually, which would result in very bad bandwidth utilization. And that's why AES-67 called for 1 millisecond packet time, because that's a good compromise of latency and bandwidth utilization. Well, if you look at this upper line here, I should be doing it like this. The upper line here, it says, okay, the lower the number of frames per packet, the lower the latency is, right? The more frames you have to wait for to acquire before you can send off the packets, the higher, of course, the latency is. So in other words, if I am gathering 48 frames before sending off the packet, it's already 1 millisecond of latency. I can't beat that. This is there before that packet even was on the network, without all the packet delay variation. And actually, in our applications, in our modern technology, this is a much more determining factor than all the packet delay variation in latency, speed of light, etc., unless you are using, telco networks on long-haul infrastructures. So packet time is a very important factor. Then sender-receiver implementation is another one. Of course, sender-receiver can be implemented in hardware with an FPGA in the background, can be on an embedded platform or in pure software. Well, with an FPGA in the background, I should be able to achieve lowest packet times and lowest latency, of course, because theoretically, I can shoot out a packet at every sample, but there is no processing delay. As samples appear, they are processed, packetized. Once the packet is ready, it's been shoot out. That doesn't mean that those implementations do not provide huge amount of receive buffer capabilities. I'll come to that in a minute. How does the receive buffer come into the game again? A typical embedded platform like the Bach Minuet from Ross, they may not be able to support all packet times, thus they have maybe have higher latency 'y because of the packet time they support. And then software implementation, there's another factor coming into game, and that's the software jitter. Because now we have interrupts in operating systems and software processing the packets, and that is an even less determinable process. And so the typical processing latencies you can observe in the context of virtual sound cards, fully software-based solutions may even go up into the 10 millisecond range. So in other words, if you have a virtual sound card sending off packets, even if they are packetized at 1 millisecond, it might require the receiver, to equalize jitter due to software in the process, on the processing on the transmitter side, up to 10 milliseconds. That's not the network, it's the processor, the way that it's implemented on the device. And then there's an application type factor, and that's the stream alignment. Now we send out just one stream to one receiver. We don't care about alignment. We want to play it back as soon as we get it, right? But if we have two different streams, having the requirement for alignment between each other, like video and lip sync or left and right stereo channel or stream, we definitely want to align them. And it may just be the case that one stream has a longer transitional time through the network as the other one. But in terms of having them aligned, we need to have the same playout time. right? So here's one case, and thanks Andy Rayner for this image. I love to take this. We have a video chain, whereas the camera, we have processing units in between. There are link times, that's the network-related stuff, and finally the video frame is being displayed. We have a microphone. Processing time from one device, and of course, apparently the audio is much earlier at the destination point than the video. So that means that the audio needs to be pulled up in the receiving device for quite a long time before the video is there and can be played out, right? And actually, we are working in a work group on how we can establish a mechanism, a system-wide mechanism, which is not directly based on all the individual in-between links of devices, because, well, of course, all these devices have buffers to cope for delay variation induced by the network. But, well, we definitely need something which actually at the end calculates the overall delay for all the participating devices due to alignment and network jitter and all the other factors we were just talking about. So, here's that game with the link offset. AS67 has described this quite nicely with a diagram. We have a sender, we have a receiver, we have a network in between, and we have the timing reference points. That's the ingress time reference point and the egress time reference point. Whenever the sender is acquiring a new sample by A to D conversion or by just sampling something in, it's basically taking a timestamp, and not to be mixed up with timestamps which occur in 1588. They don't have to do anything with the RTP timestamps we take for the audio data. Now, and what I will tell a receiver system, what is the desired link offset or latency for that particular sample, all the way from the ingress to the player, to the egress, taking into account all the things we just discussed, packet time, packet delay variation, distance, sender implementation, and so on. So that someone needs to set that link off to a certain deterministic time. Usually that can be done manually or by some means of a systems algorithm, but this is the way that we ensure a fixed deterministic playout from any sample entering the system to the point where it exits the system. And that's where the receiver packet buffer comes into game, because from the picture before, that receiver packet buffer needs to be able to be large enough to hold up any samples which need to be held up for quite a time. So a large receiver buffer capability does not necessarily mean that we have a large latency, right? Because it's just there for reasons of larger packet delay variation. So let's go back to our diagram. Now we have the RX packet stream, and how does that translate into RX playout? So the presentation of the data at the playout point. Well, we have to look at the largest occurring network delay because of network jitter and all the other factors we just observed. And we know this because we have the origination timestamps, and we can just look, what's my time, when was this been generated, what's the longest delay I'm experiencing. And now we need to take this maximum network delay plus the desired alignment offset plus maybe a safety margin. That calculates to our link offset, and I'm now telling the receiver that is the link offset for any incoming packet, and you can't start the player before the link offset has been passed with respect to the origination time point. So that's where we have the playout of the first packet. TX was sent off there, and the receiver will play it out here. And once this is in place, now the playout can happen in a very isochronous way. But it's a delayed playout, right? So that's why our flight will be delayed by 2 milliseconds. Let me briefly skip the next slides, because that is just explaining how this can be achieved with long distance, blah, blah, blah. Just going over here and going to the summary. All right, so summary. What is latency? What are the determining factors? It's the underlying network technology itself. It's the topology, it's the network jitter or packet delay variation, the stream or packet configuration, namely the packet time, it's the type of implementation in the sender and receivers, and it's a desired stream alignment among different streams. This all contributes to latency. And at the end, through the described mechanism of the link offset, we will have a deterministic and stable fixed play out. And link offset and receiver buffer are the keywords here in this. The takeaways in terms of practicality is usually we have an, let's say, 3 to 5 millisecond typical delay in an AoIP system. It can be much shorter, it can be more, but typically that's what you see in a system. However, sub-milliseconds latency is possible, in particular with, not too huge networks and hardware-based implementations where we have quite good processing power in there. And some applications also require a decent amount of receiver buffer size to being able to cope with packet delay variations, particularly in wide area applications or when alignment requirements come into game. So, and remember, receiver buffer size is not equal to link offset. A device offering a huge receiver buffer does not automatically have a huge latency. It just has the capability to deal with factors which would result in a larger latency, like wide area transport. And now, finally, guys, thanks for staying here. Here's the big surprise. Clean your brains, forget everything I told you in the last 25, well, basically 30 minutes. Forget about everything, because as I discovered yesterday evening, really, the future is actually here. We don't have to worry about any latency at all anymore. Zero latency is here, and it's registrable at the MGM grant. Go for it. Any questions?